Welcome students once again into the class of number theory, and we are doing congruences. So I'll try to prove some important results related to congruences today, and then in the next video we will apply them in several examples, illustrations and in counter examples as well. So the first one what I'm going to take is, write down, is the theorem, or you can say article, anything. If A, B, C are integers such that AC is congruent to BC modulo M and D is the GCD of C and M, then A is congruent to B modulo M upon D. This is the result we are going to prove, the first result that we will prove today. And move on to the proof now. We are given that D is the GCD of C and M. That means D divides C and D divides M. So there must exist integers K1, K2 such that your C is dk1 and your M is dk2. Now, since D is the greatest common divisor of C and M, so the greatest common divisor is taken out. For the rest of the integers K1 and K2, definitely their GCD will be K1 and K2 GCD will be equal to 1, because whatever the greatest common divisor was D, it is taken out from C and from M. So rest of for the numbers K1 and K2, the GCD will become now 1. Also, we are given that AC is congruent to BC modulo M. Using the definition of congruences, we can easily say that M divides AC minus BC, and this means M divides C times A minus B. Now what is your M? Your M is dk2. So you can put here dk2, and your C is dk1. So this dk1. Now D is common, so D can be deleted. I can delete D from here as well. So K2 divides K1 times A minus B. But we know that if A divides BC and GCD of A and B is 1, then A divides C. Here the same condition is there. K2 divides K1 times A minus B. But what about the GCD of K2 and K1? The GCD of K2 and K1 is 1. So K2 must divide A minus B. So this means K2 divides A minus B. And from here, using the definition of congruences, you can write A is congruent to B modulo K2. What is your K2 now? Your K2 from here is M by D. So substitute it here. It is M by D. And have not we completed the proof? Yes, we have completed, because what we wanted to prove, A is congruent to B modulo M by D, is proved. So in this way, you can prove this theorem. So I am moving on to the next one. There are several results we want to prove today, because these results will be used later on in examples, in theorems, in lemmas, in counter examples, and so on. The next one what I am going to prove is, write down the statement first and then we will move on to the proof. The statement is, if X is congruent to Y modulo M, then GCD of XM and GCD of Y and M are same. This we want to prove. If X and Y are congruent to each other modulo M, then GCD of X and M is same as the GCD of Y and M. And the proof is once again very easy. So let us see how it can be proved. First of all, this X is given to be congruent to Y modulo M. Using the definition of congruences, we can write M divides X minus Y. And if m divides x minus y, then definitely there must exist some integer k such that you can say k belonging to z, such that your x minus y is m times k, or you can say your x is equal to y plus mk. This will be used to show that GCD of xm and ym are same. Suppose GCD of x and m is d1 and GCD of y and m is d2. So what is left to prove is that d1 and d2 are same. So d1 is equal to d2. That is what remains to be proved. Now what is d1? d1 is the GCD of x and m. So that means d1 divides x and d1 divides m. Now if d1 divides m, then d1 divides every multiple of m, and mk is also a multiple of m, so d1 must also divide mk. Now d1 divides mk and d1 divides x. If d1 divides x and d1 divides mk, then d1 must also divide their difference, so d1 will divide x minus mk. X minus mk. Now what is x minus mk? From here you can see that your x minus mk is equal to y. So this d1 divides now y. d1 divides, I wanted here, in fact I started with x and m, I want y and m. So let me change a proof little bit. I'll again start that d1 divides x and d1 divides m. Instead of changing this, I'd like to change this. So I'll start from the same. d1 divides m. So d1 divides, this means d1 divides mk. Multiple. But I'm not going to change this. I want to change this actually. So d1 divides x and d1 divides mk means d1 divides their difference. So d1 divides x minus mk. And this d1 divides m, I will keep it. I will keep it. Now what is x minus mk? X minus mk from here is y. So your d1 divides y and d1 divides m. If d1 divides y and d1 divides m, this directly means that d1 divides GCD of y and m. But what is the GCD of y and m? GCD of y and m is d2. So this means d1 divides d2. Now change the process. Start with this one. Start with this one. That GCD of y and m is d2. So that means d2 divides y, d2 divides y, and d2 divides m. And we will move on to the same lines. That d2 divides m means d2 divides every multiple of m. So this means your d2 divides mk. Now d2 divides y and d2 divides mk. So d2 must also divide their sum. So d2 divides y plus mk. This I will be not in need of. Now what is x? Y plus mk. Y plus mk is x. So your d2 divides x. d2 divides x and d2 divides m means d2 divides their GCD also. So d2 divides GCD of x and m. But what is the GCD of x and m? Is d1. So that means your d2 divides d1. d1 divides d2 and d2 divides d1. That means d1 and d2 are associates. That means they are either same or negative of each other. But negative they can't be. Why? Because d1 and d2 are both GCD. d1 is the GCD of x and m. d2 is the GCD of y and m. So d1 is positive, d2 is positive. If two numbers are associates and both are positive, it directly means that they are same. So d1 is equal to d2. But what is your d1? Your d1 is GCD of x and m. What is your d2? It is GCD of y and m. So what we wanted to show that GCD of xm and GCD of ym are same has been proved. So this is the second theorem of the day, and now I'll move on to the next one. What the next theorem says. Since we are doing GCD, definitely it will be related to the GCD, and the theorem, the statement of the theorem is write down the statement and then we will move on to the proof. Statement is, if A is congruent to B modulo M and 0 is less than or equal to mod of A minus B is less than M, then A and B are same. Proof is very easy, without any doubt. So let us move on to the proof. A is congruent to B modulo M. This means M divides A minus B. And if M divides A minus B, then M must also divide its modulus. So that means M must also divide mod of A minus B. And mod of A minus B is strictly less than M, but is greater than or equal to 0. We know that no positive number can divide any positive number strictly positive greater than 0. No positive number can divide a positive number less than it. So M cannot divide mod of A minus B till A minus B mod is equal to 0, because the 0 is the only possibility for which M can divide mod of A minus B. So this means mod of A minus B is 0, and from here you can say A minus B is 0, which means A is equal to B. So if A is congruent to B modulo M and their modulo difference lies between 0 and M strictly less than M, then A must be equal to B. This one result will be used in proving another result which we are going to prove now. What the result is, first write down the result and then we will move on to the proof. The next result what we are going to prove is that if A is congruent to B modulo M, leave if from here, A is congruent to B modulo M if and only if AB have same remainder when divided by M. When divided by M. So I am moving on to the proof now. Suppose R1 is the remainder. Suppose R1 is the remainder when we divide A by M. So when we divide A by M, there will be some quotient Q1 and remainder we have supposed as R1. So your A, you can write A as M Q1 plus R1, where remainder R1 is greater than or equal to 0 but is strictly less than M. Similarly, suppose when you divide B by M, quotient is Q2 and remainder is R2. So B can be written as M Q2 plus R2, where R2 once again is greater than or equal to 0 but is strictly less than M. Looking at these two conditions, we can very easily conclude that the mod of R1 minus R2, since it is mod, it is greater than or equal to 0 but is strictly less than M, because both the numbers R1 and R2 are less than M. If two numbers are less than M, their difference can't be greater than or equal to M. It must be less than M. So once again, you are given that A is congruent to B modulo M. A is congruent to B modulo M. What is your A? Your A is M Q1 plus R1. And what is your B? Your B is M Q2 plus R2. Since we are having modulo M here, from this congruence equation, wherever you get a multiple of M, you can delete it. So it is a multiple of M, can be left. So I am leaving this MQ1, and this MQ2 is also a multiple of M, so I am also leaving it. So what we are left with? We are left with R1 is congruent to R2 modulo M. R1 is congruent to R2 modulo M, and the modulus of R1 minus R2 is greater than or equal to 0 but is strictly less than M. And from the previous theorem what we have proved, we can directly conclude that this means R1 is equal to R2. What is R1? R1 is the remainder when A is divided by M, and R2 is the remainder when B is divided by M, but they are coming out to be same. That means A and B will leave the same remainder when divided by m, and that was the required result to be proved in this theorem. So I am moving on to another theorem. So what the next theorem says, just write down the statement and then the proof will be provided. Theorem is A is congruent to B modulo m and A is congruent to B modulo n if and only if A is congruent to B modulo LCM of m and n. Here I would like to tell you that for GCD of m and n we use this symbol, the round brackets, and for LCM of m and n we use the square brackets m and n. So this is GCD of m and n and this is LCM of m and n. So the theorem says A is congruent to B modulo m and A is congruent to B modulo n if and only if A is congruent to B modulo LCM of m and n. And let us see what the proof says. So first I am going this way, and since it is if and only if, I will also have to go this way. So first I suppose that this is given, that is A is congruent to B modulo m and A is congruent to B modulo n. This is given. From the first one you can write m divides A minus B. From the second you can write n divides A minus B. Now A minus B is a multiple of m and A minus B is a multiple of n. That means A minus B is a common multiple of m and n. But what is this? LCM. LCM is the least common multiple. A minus B is a multiple, common multiple. A minus B is a common multiple, but this is least common multiple. So least common multiple must divide every common multiple. So that means this LCM mn must divide A minus B, the common multiple. And from here you can directly write A is congruent to B modulo LCM of m and n. And in the same lines I can prove converse very easily. Conversely, we are given that A is congruent to B modulo LCM of m, and this is given to us now. And it directly means that LCM of mn divides A minus B. This is least common multiple. Least common multiple is a multiple as well. So it is a multiple of m, it is a multiple of n. That means your m divides LCM of mn, and similarly n will also be. Now m divide LCM mn, LCM mn divides A minus B, and this relation of division is a transitive relation. If A divides B and B divides C, then A also divides C. We have proved in a previous video. So here m divides LCM of mn, LCM of mn divides A minus B, directly means m divides A minus B, and this means your A is congruent to B modulo m. Similarly, your n divides LCM of mn, once again because mn is a least common multiple of m and n. Least common multiple is a multiple as well. So this is a multiple of n, so n divides it, and it divides A minus B because of the given congruence. Now once again A divides B and B divides C, and using the transitivity of the relation we can say that n divides A minus B, and that means A minus B is congruent to A is congruent to B modulo n, and that is what the result wanted to be proved. And another theorem, another result which is once again important, will be used in the coming theorems. So write down the statement and then enjoy the proof. Theorem: if A is congruent to B modulo m and D divides each of A, B and m, then A upon D is congruent to B upon D modulo m upon D. And you will enjoy the proof, as it is very easy, it is very interesting, and let us see how to prove it. We are given that D divides each of A, B and M. That means D divides A, D divides B, D divides M. This is given. So there must exist integers k1, k2 and k3. There must exist integers k1, k2, k3 such that A is equal to dk1, B is equal to dk2 and M is equal to dk3. Now you are also given that A is congruent to B modulo M. So A is congruent to B modulo M means your M divides A minus B. And substitute the values for M, A, B from here, from this line. What is your M? Your M is dk3. So dk3 divides A minus B. A is dk1 minus B is dk2. You can take D common from this term. So you can write D times k1 minus k2. A multiple of D divides a multiple of D is always obvious. So that D can be removed, can be deleted, can be omitted. So deleting D from here, what you are going to get, that K3 divides K1 minus K2. And if K3 divides K1 minus K2, you can easily write that K1 is congruent to K2 modulo K3. But what is your K1? Your K1 from here is A upon D. So this is your A upon D is congruent to, what is your K2? Your K2 is B upon D. So it is congruent to B upon D modulo K3. And what is your K3 is M upon D. So the required result is obtained that if A is congruent to B modulo M and D divides each of A, B and M, then A upon D is congruent to B upon D modulo M by D. So I am going to stop this video here. In the next video we will have several examples, counter examples, illustrations based on these theorems, these articles, these results. So till then, thank you once again.